Sound check. We're good. Okay, so I want to imagine that we're talking it's 5,000 years ago. We're talking a long time ago. 3000 BC. You guys know what 3000 BC means? You guys know how like that timeline works? Yeah, if you don't know, it basically if you had a timeline, we are currently in the year 2018, right? And the way that we've just broken up time is this is like BC and this is AD. Sometimes this is referred to as before Christ. This AD is like it's Latin for something. It means in the year of our Lord. So anyways, that's the breakdown. It actually, although people say that, it actually there's a Latin for it. It's something diminutus or something like that. Anyways, you don't need to worry about that. If we're talking 3000 BC, there's like 3,000 years from here to here, and then 2,000 years from here to here. Does that make sense? So we're talking 5,000 years ago, basically like as far back as we can imagine. Were there scientists back then? Well, I don't know that maybe scientists in like the traditional sense of the word scientist really makes sense because they didn't wear lab coats and have glasses and work in labs, but were people exploring things and playing around with chemicals and trying to make new stuff? Absolutely, right? And so one of the words we would use is this one here. It's called metallurgy, where basically old-fashioned, let's call them scientists, let's call them chemists, they were trying to make metals. Now, 5,000 years ago, why would you need metals? I would say there are three main reasons why you would need a metal. And I even have actually I have them all listed here. One of the reasons why you might care about metals is because it was jewelry. And it was like a form of currency. If you had gold and you had silver, that was how you had wealth, right? And even way back then, there are records that people had coins. They had ways of keeping track of money in that sort of way, right? They bartered with their cattle and with their livestock and stuff like that, right? But I mean, if you had jewelry and stuff like that, that was valuable. That was one reason you might care about metal. Okay. Here's the other two. Tools. What sort of job might require tools 5,000 years ago? They didn't have railroads back then. How about this? Farming, right? Let's say that you needed to plow a field. You didn't have like a John Deere tractor. You had an ox, right? Or some sort of cattle, depending on where you lived. You still didn't have John Deere though. Not 5,000 years ago, right? And so you may have like a big rock that you'd plow behind it, right? But what if you're the first person who uses a piece of metal and you make like a spade, you make a shovel out of it? Does that make sense, right? If you can make some sort of tools out of metal, that's really good. And here's the last thing where you might care about metal, weapons. Unfortunately, humans in their history have not exactly been nice to each other. We have fought, there have been wars, countless wars, and in general, war has always followed scientific breakthroughs. Let me give you some examples, and some of these are not necessarily, these aren't about metal, but like I'll give you some good examples. In about 1945, World War II was going on, and World War II ended with the culmination of something called the Manhattan Project. I told you, today is story time with Chris. Anybody ever heard of the Manhattan Project? What did the Manhattan Project make? Anybody know? It was the first nuclear bomb, yeah. And the first nuclear bomb was actually, well, two of them, they were dropped in Japan. And that's actually what ended kind of officially World War II, is the United States dropping two nuclear devices, the only two that have ever been detonated like in a wartime setting in the world, and like it devastated some towns in Japan, like huge catastrophic deaths, right? And really, that war kind of preceded the idea of like technology. Go back to previous World War. World War I, one of the technologies that was used was chlorine gas, mustard gas. And they literally tried to poison and choke each other by like gassing each other across fields, right? The first person who discovered gunpowder, that changed the way that you fought too, right? Steel would be another good example. If we're talking the medieval ages, so imagine you're talking like the Knights of the Round Table and you're in like the full get-up suits of armor, right? Well, if somebody else is fighting with like, say, a stick, and you have like a full suit of armor and a sword, who wins that fight? Yeah, the guy with the suit of armor, right? And so really, weapons have always really been based on scientific advance. So if I can go way back now 5,000 years ago, I mean, we're talking people who were fighting with, yeah, like if you were the first person to be able to make a shield because you were able to mine and work with copper for the first time, and the guy you were fighting against didn't have a shield and you had a shield, who's going to win, right? If you're able to make an arrow with a nice, refined, pointy arrowhead, and the other guy has like a rock as the arrowhead on their arrow, you know what I'm saying here? So anyways, that's where we're starting. We're starting with people working with metals. And really what they were trying to do is basically find the metals in the ground and refine them and try to use them for something. So here's the metals we knew of back then. Gold and silver were usually used for like jewelry and like precious metals. Iron and copper and lead were more used for your tools and weapons. Okay? But later on, people discovered how to use things like tin. And as soon as tin was discovered, they learned how to make something called bronze. By itself, copper, not bad. But you know one of the problems with copper is that it can rust, it can flake, and it can break and corrode over time. But take copper and melt it with tin in like a forge. You guys know what I mean by that? Like where you heat it up really, really hot, and like you could literally like see it in like a liquid format, right? Melt these two metals together, and all of a sudden you make something called bronze. That's an alloy. And I mean, the Bronze Age, we actually have a phrase for this. We call it the Bronze Age. Well, all of a sudden, if you had access to bronze and somebody else did not, you had a huge advantage over them, right? Whether it was farming, whether it was warfare, right? The first guy that has a bronze shield and the other guy's trying to fight you with something made of copper, bronze is stronger. Does that make sense? So that's kind of where we're starting our story. And although you may not think of these guys as scientists, in a way, they were the first people who were trying to like manipulate chemicals to do something interesting. Okay? Eventually, we have something even better than bronze. Iron and carbon were put together to make steel. And we still use steel to this day. Let me give you some examples of where steel is really useful. Your car should have a frame on the inside of it that hopefully is very strong, probably made of steel. This building should have big like girders, big thick pieces of metal, like as support beams. That's probably steel as well, right? And when I'm talking about it here, now I'm starting to talk about like medieval times though, where like now you had knives and armors and swords. So we're talking like, I don't know, maybe more like 600, 500 years ago. Right? When they discovered how to make steel, that really changed things. And I like this photo. This would be a good example of like a metal worker or like a blacksmith. Right? Can you guys kind of imagine living, you know, in the medieval times? Maybe you've read stories or talked about this, right? Everyone had a job. Many of them ended in smith. Not because your last name was Smith, but because you were like a goldsmith or a locksmith or a, you know what I mean there? Right? And so if you were a metalsmith, right? I'm thinking of like Pirates of the Caribbean. You know, like if you've seen that movie. You guys seen Pirates of the Caribbean? Is that too old for you guys to have seen? Right? Where like, what's his face? Orlando Bloom as the one guy, he's like, you know, it's his job to make swords, right? If you're a forger of swords, right? That's what I'm talking about here, right? Okay. Now, back at this time we're talking about, the scientists, the people that we're discussing, they were really just like, they were experimenting, right? They were playing around with metal, but they didn't really know what they were working with. They were just, hey, this works really good. Let's keep going. Okay. Well, around this time frame, we've still got philosophers. And so these people, we're talking still like thousands and thousands of years ago, people like, say, Aristotle. You guys have probably heard of Aristotle before. He was an ancient Greek philosopher. And although he wasn't necessarily the person who was making swords or making tools, he had this theory. He was trying to figure out what matter was made of. Right? That's really the question, is like, what is our stuff made out of? Right? If I could zoom in, what does it look like? And so Aristotle put together one of the first theories that we know of as to what stuff was made of. And he was like as wrong as you could possibly be. He thought everything in the world was made of fire, earth, water, and air. That was his logic. He thought that those were like the four fundamental like things in the world. And so like humans are like half earth and half water. Does that make sense? And like a tree is half fire, half earth. The reason why it's half fire is because you can light a tree on fire. And you can make like a fire out of wood. Right? That was his logic. He wasn't even close. Okay, first of all, fire is not even matter. What is fire? Energy, yeah. So that was wrong. Earth, water, and air, kind of close, but like, no, that's not true. Here's another guy. He doesn't get nearly as much publicity as Aristotle does, because out of curiosity, who's heard of Aristotle before? Okay, a few of you. Who's heard of Democritus? Oh, really? Cool. Okay. Most people haven't heard of Democritus. He had a theory. He thought that all matter was made up of tiny particles that you could not cut up. Basically, his thought was, if you could try to take, like, imagine you had a cookie, and you cut a cookie in half, and cut it in half again, and cut it in half again, and cut it in half again, until you get to, like, the smallest little crumb. And then you took, like, a knife, the best knife you had, and you cut it in half again and again. He figured that at some point, you can't cut it in half anymore. It's as small as it can get. Does that make sense? Right? And so he coined a term that we still use to this day. He coined a term called atomos, which is Greek for indivisible. And he figured that stuff must be made of something called atoms. And atoms is basically the smallest particle that's possible. If you try cutting it in half, you can't cut it in half anymore. We've actually since discovered that we actually can cut atoms in half and find smaller things. They're called subatomic particles. And scientists are still trying to figure out what those are made of and what those are made of. So if you've ever heard of string theory is the most recent idea, is like maybe everything in the world is made of little strings that vibrate. And if we can ever prove that, I bet you they'll be trying to figure out what the strings are made out of, right? So, but yeah, that's pretty cool that he was the first guy. And we're talking like, again, 5,000 years ago, that he thought of the idea of an atom. We still use that word to this day. Now, I want to fast forward quite a while here. We're, again, talking like in the Middle Ages, medieval times, right? Like the 14, 15, 1600 type area. There were people who, they knew stuff about science, but like they were trying to combine science and magic, like sleight of hand and trickery, right? And what they were really trying to do is they wanted to try and make gold. Because really, like everyone wanted to be rich, right? And they had this idea. They wanted to try to turn lead into gold. Because here's the thing. Lead's easy to find. Lead's cheap and not valuable. Gold is rare, and gold we make our jewelry out of. And so they figured if we could turn our lead into gold, that would make us rich. And they tried all sorts of fancy experiments, and sometimes they were like con artists maybe in a way, where they try to like fool people into thinking they had gold. And that's probably when things like, you guys have heard of fool's gold? Right? Where like it looks like it's gold, but it's not really. They were probably doing stuff like that. They were trying to like convince people, here, buy this, right? So they were kind of like scientists, but like it wasn't necessarily a real science, but they did help a few things. There's a few notes that the alchemists did. They actually discovered hydrochloric acid, one of the first acids that we use. And they also discovered how to use lab equipment like glassware. I want to talk about that for a bit. Before putting things in glass containers, does anybody know what you would have like stored your stuff in? Pails, yeah. Maybe like a clay pot, right? You might have used clay, pottery. Does that make sense? You might have used a chest made out of wood. But here's the problem with all of those things. They could contaminate, and they could like leach the container into your stuff. Does that make sense? Like, I would not want to store my food in the fridge in like a clay pot. Does that make sense? Because like the clay would kind of like dirty up my food and it would kind of get kind of grungy, you know what I mean? But if it's all you had, I guess you'd go with it, right? But the discovery of glass, that changed things. We use glass and plastic as a lot of our storage container stuff because the container doesn't like contaminate what we put inside. Does that make sense? And so that was actually a big advancement because prior to that, science was always a little bit like muddy, like literally muddy, because the clay or the pewter kind of jars you'd store stuff in, they would make it dirty a little bit, right? So yeah, don't need tests, just go. Just put your name on the board. Okay, here's one of the first scientists I need you guys to know about. Again, story time with Chris Day. His name is Antoine Lavoisier. I don't need you guys to know how to say it, but he was French. It's Antoine Lavoisier is how you say his name. Not that you probably care that much. And he made a really important discovery. One of the most important scientific discoveries that we still talk about to this day in virtue science courses. He discovered through some experiments something called the law of conservation of mass. Basically, here's how I can kind of put this into words that are a little more, I don't know, that make more sense. He took chemical A and he weighed it. And he put it on a scale and he discovered that it weighed, let's say 20 grams. And then he took chemical B. And he weighed chemical B on the scale, and it weighed, say, 40 grams. And then he reacted them together in a chemical reaction. And so as chemicals A and B, they reacted and they formed a new chemical. Let's call it chemical C. Well, what he discovered is that it weighed 60 grams, because 20 plus 40 equals 60. And he did this over and over and over again. And every single time he did a reaction, he weighed what he started with, he weighed what it made, and every single time, whatever it started with weighing is what it ended with. And so he came up with this idea, this theory. And really, over time, we've been able to prove this theory over and over and over again. And basically the way it works is that if a theory can be proven consistently, we now call it not a theory, but we call it a law, right? Something that we know to always be true. It's called the law of conservation of mass. The idea being that mass is neither produced nor lost during a chemical reaction. Now, this actually makes a lot of sense, because if we could lose mass, slowly but surely our universe would shrink and shrink and shrink, and it would decay away, and eventually there'd be nothing left. Does that make sense? Right? If we could somehow start with 100 grams, and chemical reactions take place, and it drops down to 99, and then 98, and then 97. If we could actually somehow lose mass, eventually there'd be nothing left. Does that make sense? And maybe when you're thinking of chemical reactions, you're thinking of big flashy ones like we do in the lab. But your body is currently carrying on millions upon billions of chemical reactions right now. For example, you're breathing. That's called respiration, where you're breathing in oxygen and sending back out carbon dioxide. Every time you do that, there's a chemical reaction. Well, imagine that if what you breathed in was 100 grams and what you breathed back out was 20 grams. Well, slowly but surely, there'd be nothing left in the world, right? And then the opposite would be true. What if we could somehow gain more mass? Well, then the Earth and the universe would just keep getting bigger and bigger and bigger and heavier. And you know what would happen is everything in the universe would be turning into infinitely dense things like black holes and supernovas, and that doesn't seem to happen either. So he was the first guy that kind of discovered this concept. Okay? He also made some other contributions that we want to note. He was the first person who said, hey, let's use a common vocabulary. And we're going to learn this common vocabulary in a couple of days. Not yet, but we're getting there. But he's the one who kind of said, hey, we should all call the same thing the same thing. Right? You guys have a name. My name is Chris. It would be very confusing if someone called me Bill, somebody else called me Phil, and somebody else called me Chris. It's kind of good that I just have one name. And I know we can have things like nicknames or pet names, and maybe you have a long name and a short name. But before Lavoisier, everybody just kind of called stuff whatever they wanted to call it. Does that make sense? And he kind of came around and said, guys, let's get on the same page here. Let's use the same words for everybody. And so we came up with a system for how to name stuff so that we could talk about the same thing in Canada as we do in the States, as we do in Australia, as we do in Russia, as we do in Japan. So in theory, everyone's talking the same thing. There still are some slight differences depending on which region in the world you're in, but it was good. So because of this, he's often known as the father of modern chemistry, because he kind of got things going, so to speak, so that we could do stuff from there. The next guy I want you to know about, his name is John Dalton. And he was also thinking that one question of what is stuff made of? Right? The age-old question of what does it look like if we zoom in? But I got to point out, this is still before we had microscopes, and this is even before we really even had magnifying glasses that were any good. So we did not have the tools to zoom in and look at stuff. And the magic school bus is not real, so you couldn't even hop on that and zoom in. You know what I mean? So everything that he thought was just a theory. He had no way of proving it. But he wrote a paper and he said, hey guys out there, I think this is what our stuff is made of. Okay, there was no Twitter, right? So he wrote it down and he published it and he said to other scientists, here's my ideas on what the world is made of. And I'd like for you guys, if you could, if you're writing this down, if you have this in front of you, you should really put a star next to this. Because I know for a fact that I have a test question on this. I'm going to ask you about John Dalton's model of the atom. So make a note, study this for a test. So let me tell you a little bit about his model for the atom. He kind of actually stole an idea from Democritus. He stole Democritus' idea, and his first point was he thought that everything in the universe was made of small, indivisible particles called atoms. And basically, we use this picture as a model. He figured that it was like a marble, or like a ball of some kind. and that you could not cut this in half. Even if the ability was there, you could not take a saw and cut it in half. That was impossible. This is like as small as it gets. The analogy I like to use is my daughter likes to play with Legos, right? And so we make the Barbie dream house out of Legos, and she's got all the little characters there, all the minifigs, right? But like at the end of the day, the smallest piece of Lego, like I can't cut it in half. I can take two pieces of Lego, rip them apart if they're meant to separate, right? But like at its core, there's got to be like a smallest piece out there. Right? In biology, we call that a cell, by the way, right? Like there's nothing smaller than that. So that was Dalton's idea. He was actually wrong on that. People later discovered what are called the subatomic particles, protons, neutrons, and electrons, and I'll get to that. But that was his idea. He had another idea. He thought that every element, all atoms of an element, they were completely identical. So if you had a ball of hydrogen, you had a second ball of hydrogen, and you had a third ball of hydrogen, what he thought is that each one of these was an exact clone of the other ones, that they were exactly identical in every single way. They weighed the same amount, they were the same size, they looked the same. That was his theory. He was actually wrong about that too. Now I can't explain why just yet, we'll get to that. But he was actually wrong about that as well. He didn't know that there were actually different weights you could have. Next thought. He figured that different elements should have different properties. So if you had a hydrogen atom ball over here, and you had a carbon atom ball over here, he figured these two things should look different. Okay? If this one's hydrogen, and it looks the same as something else, like these ones that look the same, they better all be the same thing. And if these ones look different, they better be something different. And he was right about that one. And then the last one here is kind of tough to explain, so I'll use an example. He figured that elements can combine to form new substances. Let me give you a classic example. H is for hydrogen. And he figured that the hydrogens don't just stick by themselves. Maybe they can form a bond with something like oxygen, and maybe even back to a hydrogen again. And they can form compounds. What do we call this compound? Yeah, this is H2O. It's water. And so he figured that like these individual little balls, they actually have the ability to combine and make bigger stuff. And he was right about that too. And so he's the first guy that we at least have a record of that kind of wrote down his thoughts and said, here's what I believe stuff's made of. He had no reason to know that was true or not. This is what he figured was the case. I don't know that I can even call him a scientist yet though. Because for it to really be a scientific process, there's really four things you have to have. You have to have a hypothesis. He had that. He had an idea. But then you have to design an experiment to test it and collect some data. Then you have to analyze that data, and then you have to like re-look at your first assumption and see whether or not it was right or not, and then revise it. And he didn't have the ability to do that because he didn't have microscopes yet. So he wasn't really doing scientific method just yet. Another scientist I want you guys to know about. His name was Dmitry Mendeleev. Dmitry Mendeleev. And he's pretty famous. People sometimes know his name because he's the person who decided, let's start categorizing all the elements we know of. Here's what he did. The legend goes that he wrote down all of the known elements in the world on cards. And he wrote down how heavy they were, and he wrote down some of their properties. And he started like putting like similar things together. Kind of like my daughter, she's in kindergarten, the one in preschool, like she comes up with the most amazing connection. She'll be like, Dad, these two things are both purple. And like the two objects we're talking about could like not be more different. Like one could be her shirt, and the other one could be like, I don't know, a book on the other side of the room. And she'll be like, they're the same, they're both purple. You know, and like she's 4, right? So it's adorable. You get what I'm saying though? That's kind of what he did in a way, where he started looking at like some generic things, and they're like, wow, these guys are kind of similar, and these ones are similar. And he started to like combine things together. And he made really what I would say to be as the first like scientific idea. He had a hypothesis, and then he wanted to start being able to test it. So he started putting things into like a grid. He said, okay, these guys kind of go together, and these guys go together. He started putting a grid. And here's the cool thing. He actually left some gaps in his table. And he said, I think that one day we're going to discover this element. He basically said, whatever should go here, I don't know what it is yet. And he made a prediction, which is what science should do. He predicted one day we're going to find what goes in this hole. You know the amazing thing is that that's exactly what happened. Here are 4 elements, that Mendeleev predicted would fit into his table that we one day found, which is so cool that he'd be able to make that prediction. And so he actually was the first person to make what is behind you guys over here, the modern day periodic table, where we start putting things in rows and columns. And we're going to talk about that more another day. We're kind of building our way to that, but we want to give credit to him for making that prediction. That's pretty cool. Okay, now here's maybe the first guy that I can start talking about who really did the scientific method well, though. He had an idea. He designed an experiment. Through that experiment, he analyzed some data, and then he revised his idea. So I want to talk about the climate at the time here. Up until the point that J.J. Thomson did his experiment, people thought that matter was literally like a marble, and you could not cut it into pieces. That was as small as it got. It was like the marble model. Okay. Thomson made an experiment, and I don't need you guys to fully get the experiment. I can explain it better in more detail if you like, because we actually, this is physics 20 and physics 30 we talk about. But let me see that I can kind of explain the basic concept. This thing right here is called a cathode ray tube. This is called a cathode ray tube. Sometimes we abbreviate it as a CRT. We actually still use these today. They're less common, but we used to use cathode ray tubes in old school TVs, not the flat screen ones. You guys know the TVs that are the big box? Those would have had cathode ray tubes in them. And that's actually what made the picture on the screen. Here's basically the idea. What it does is there's a battery source, there's an energy source right here, and it shoots a beam of particles called cathode rays. And it shoots those beam of particles through this tube. And what they do is they put some magnets here, and they put some voltage plates. And depending on how they mess around with the magnet strength and the plates basically, you can make these particles kind of deflect up and down and to the side, which is kind of weird, because you could actually make them veer off course. Now, there were two things that were noteworthy here. The first thing that was noteworthy is that these particles that went in here, they were 1/1000th as big as the smallest element they knew of, which was hydrogen. Up until that point, the smallest thing they'd ever heard of was hydrogen. And these particles, when they weighed them, they were 1,000 times smaller. And there was one more thing about them that was really weird. Because they deflected, they must have had charge to them. So I'm running out of room here, but I'll write that out here. Because they veered off course up and down, it meant that they were charged. And this kind of implied something. It implied that there must be something smaller than hydrogen. Hydrogen was thought to be the smallest thing out there, and not only was this new particle a cathode ray, not only was it smaller, 1,000 times smaller, but you could actually bend it if you knew how to use magnets and electricity properly, which is kind of cool. You know what J.J. Thomson discovered? We don't call it a cathode ray anymore. Oh, it's right on my slide here. He actually discovered the electron. We didn't call it that back then. He actually called it a cathode ray, but he had actually discovered the first subatomic particle. And this blew a big hole in Dalton's theory, because Dalton basically thought that this ball back here was the smallest things could be. Well, now Thomson has evidence that there is something that is that small, and not only is it 1,000 times smaller, but there's charge to it. It's positively or negatively charged. So he had a new theory. Thomson, again, there's no Twitter, right? So he wrote a paper and says, guys, I have a new theory about what stuff is made out of. He figured that maybe it's like a ball. But inside that ball, there's little bits of stuff. And those little bits were those cathode rays. Only we don't call them cathode rays, we now call them electrons. And he figured that because those cathode rays were charged, they must be negatively charged. So he figured that all these things here were negatively charged. And this basically means that now an atom is the wrong word for it. Because what does the word atom mean? Indivisible. And yet now there seems to be evidence that there actually is smaller stuff inside of it. Now we couldn't look at it with a microscope, but it sure seems to be the case that because it can bend these rays, right? These rays could bend up and down. This seems to be the case. He actually used an analogy of a very famous dish at the time. We don't really use it much anymore, but it was called plum pudding. Basically, the way plum pudding works is that there's this doughy bread, and inside it are raisins. And the idea basically would be that the raisins would be like the little electron bits, and like the bread, the doughy part, that would be like the pudding, so to speak. And he uses it as an analogy. Sometimes you even see it drawn like, ooh, that's not what I want. Go away. Sometimes you even see it drawn like this. I don't have the picture on here. But you see like a sphere, and what you do is in the middle, you kind of make it positively charged in the middle. And then around it, you have all these little bits of like raisins. It would be like a fruit cake or something like that, where there's little bits of fruit inside. And that's what he figured that the model of the atom looked like. And you know what? He was kind of right, because electrons do exist. He wasn't fully right, but his ideas were good. Like I said, it's story time with Chris today, hey? Then I want to fast forward and tell about the year, I forget it exactly, but I think it was 1907. And so this is actually very recently. Now again, we were only just starting to get microscopes and tools that could really zoom in really close. This guy named Ernest Rutherford, he designed another experiment trying to figure out what stuff is made of. And this one's really cool. I'm going to try to describe it on a new slide here. I'm actually going to go to the front of the room. I'm going to go mobile here and describe this. Here's what Rutherford did. He set up an experiment where he had like a sheet of foil. It was like gold. Okay? And then he had a machine that shot objects at it. And so imagine these are like particles. He threw objects at the machine. What would you expect to happen as you shoot objects at a wall of something? They would just hit it and bounce off, right? That's not what happened. That's what makes this so amazing. Here's a picture of his experiment. He shot these particles right here at the gold, and you would think they would bounce off. And you know what ended up happening? They phased right through, which was like, how is this possible? Like, this is like mutants that can like phase through walls. It made no sense that somehow these particles could go through. And so Rutherford had a new idea. He figured that rather than the ball looking like this, and like if you imagined matter, let me draw a new picture here. It would basically be like a ball next to a ball, next to a ball, next to a ball. And if you tried to shoot something at it, could it go through? Well, no, it would hit this and it would bounce, right? Just like when I threw something at the whiteboard, you figure it would bounce off, right? Right? And so this wall of particles, that's what they used to think happened. Rutherford had a new idea. He figured maybe there's something called a nucleus, where all of the positiveness is all kind of in the center. And then around it, the electrons are on the outside. And this was kind of a fundamental shift, because before that, the model of the atom was that the electrons were inside the ball. He kind of figured, what if it looks more like this? Let me try to, well, this picture is about as good as one of them I'm going to get. He figured, what if all the positives were kind of in the middle and the electrons went outside of it? Now let's revisit that model. So you know how I had this picture right here? Where if I tried to throw something at it, it would just hit it, right? What if I make a slight tweak now? What? Ooh, that was weird. What if, rather than the first two, what if it looked like this? What if all the positive was right there and the electrons were outside of it? And what if the next one, all of the positive was kind of in the middle and the electrons were outside of it? Now what would happen if you shot a particle at it? Can you kind of see how now it would like phase right through? Because there's gaps there. And he coined this term, the nucleus. He figured everything was kind of shoved in the middle. He actually used an analogy called the planetary model, where he kind of figured, if I can go back to this picture here, that this was kind of like the sun, and then these were planets going around it. Because they knew at this time, by the way, that the Earth went around the sun, not the other way around. So they figured this is like Mercury, and this is like Venus, and this is like Pluto and Neptune, and right? And so they figured this is the center, and everything kind of orbits around it. And the next one would be over here like this, and it would also have some orbits around it, and you could literally phase through. And it also explained one of the weird things, is that once in a while, occasionally, a particle would hit the gold foil and bounce backwards. Most of them would phase right through, but some would bounce backwards. It actually explained that, because the idea would be that like you'd expect them all to phase through, but if most phased through and some bounced, what that really meant is that if you have this nucleus with electrons kind of like going around it, and another nucleus with electrons going around it, as you try to like phase something through, here, that line made it right through, right? That line made it right through, but hey, this one right here, it'll bounce off to the side, and this one will bounce back. So it actually kind of made sense. One more cool thought. Rutherford was actually Canadian. Oh, actually, no, he wasn't Canadian, but he worked in Canada for a good part of his life. So we kind of get to take credit for him a little bit. He worked at McGill University in Quebec, actually, which is kind of cool. So now, here's the problem with Rutherford's model of the atom, though. Although he believed in this nucleus idea, he actually knew it was wrong immediately when he made the theory. And the reason why he knew it was wrong was due to some physics work that had been done about 50 years beforehand. In physics, if you guys go that far, and I'll teach you that maybe in 3 or 4 years, okay, there's an idea, you guys have heard of like radiation before? Okay, like there's a bunch of different types of radiation, like there's X-rays, there's radio waves, there's light waves, gamma rays. You guys have heard of some of these before? Okay. There is a theory that we believe to be true, that basically any particle that is charged that goes around in a circle, it gives off radiation. And what that would mean then is that if these electrons actually did like go in circles, just like planets go around the sun, 2 things would happen. 1, not only would these particles give off radiation, and we would all be dying, but 2, the particles would then lose energy, and they would eventually spiral into the middle and crash into the middle. And so Rutherford, like as soon as he made his theory, he actually knew it was wrong. So he didn't quite know how to make it work perfectly, but like he knew that this model here, the idea of it being like a ball with like stuff inside, he knew that was wrong. He wasn't sure exactly how it worked, because again, he couldn't like zoom in with a microscope. We actually still can't even zoom in with a microscope, by the way. It's actually not possible for us to get that in depth. So, but this is his new theory, the idea of a nucleus. Okay. 2 years later, it was actually not that long. It was in the year 1909 or 1911. I always forget. It's 1907, 1909, or 1911. It was like 2 years later. A friend of his, a colleague, Niels Bohr. You pronounce this not Neil, but Nell. That's how you pronounce it. Anyways, Niels Bohr was working on a similar experiment, trying to figure out like what was this stuff made of. And he had a new proposal. He thought that maybe the electrons were on the outside still, but he figured they didn't go around in circles. He came up with this idea of energy levels. And he figured that the electrons exist in these like, not orbits where they go around in circles, but in levels. We still sometimes draw these pictures as though they go in circles. Like a common picture would be to do something like this. Draw a nucleus with a whole bunch of stuff in a nucleus. And when we draw a circle like this. Okay. But here's the fundamental difference. Rutherford would have thought that this electron, I'll use an E for electron, Rutherford thought the electrons literally went like in a circle. That was the best he could think of. He knew it didn't, but that was his thought. Here's what Bohr thought. Bohr thought that the electrons live in these like levels. And if they want to move, they go from this level to the next ring. You guys know like how there's rings on a tree? Picture rings on a tree. And he figured the electrons don't travel in circles this way. That's wrong. He figured that electrons literally jump from here to here and then from here to here. But here's the weird thing. He actually is predicting teleportation. He figured that the electron was here and then just shows up here. He predicted that we would never find the electron halfway in between. He figured it would either be in this ring, and if it wanted to move, it would instantly just jump and hop right from here to there, which we actually believe to be true. Like science fiction stuff about like teleportation and stuff, there are actually physicists in the world right now who are working on teleportation because we actually seem to have evidence that that's how electrons move. You don't find an electron go from here to there. You know how I've got these guys in like rings right here where there's like a semicircle? If I had to go from here to that set of desks, I would actually have to like walk to get there. Evidence exists that electrons literally go boom, boom, and they just show up there, which is like so crazy cool stuff. And I'll tell you more about this if you care, because it's like physics, which is like my passion. But that was his idea. Now, I can't probably explain this very well with what you guys know to this point, but here's the evidence as to why he believed this. He was looking at something called a spectrum. And what ends up happening is he was able to get these bands of light. And you can probably hardly even see them in this picture, but you guys can see the little red band of light right here. And you can see this little maybe purple or blue band of light right there. And there might be one that's over here somewhere, but it's really, you can barely even see it probably. This evidence to him suggested that the electron used to live right here. I'll use a new color. And that the electron literally jumped from here to there and then to there. And each time it jumped, it gave off a new color of light. That's what made it jump. And the reason why it literally is like teleporting is that there is no color in between there. That was his theory. And so we call those energy levels. And yeah, we actually believe this to be the way the world works. Electrons literally just like jump from one place to the next. So it's cool stuff. I'll tell you more if you care. Because it's really, I'm getting a little bit beyond Science 9 right now. So this is actually kind of a good picture of what a Bohr diagram would look like. So I need to make it clear, this is very similar to Rutherford with a key difference. Rutherford thought that these electrons went around in circles. And like I said, he actually knew they didn't. Because if they did go around in circles, it would give off radiation, and they would eventually lose energy and spiral into the middle. And you'd actually have like, this guy would eventually like spiral into there. And this guy would eventually spiral into there. And like, literally like the world would start collapsing on itself. So he knew that was wrong, but it was his idea. Rutherford's idea is, yeah, the electrons are still outside, and like you would never, ever, ever find an electron right here. That was his theory. It would literally jump directly from here out to there. And it doesn't even have to be like from here to here. It could jump from here over to there. Like it could actually teleport long distances. Einstein actually spent a good deal of his life working on stuff like this. He called it action at a distance. He actually called it spooky action at a distance, actually. He actually used the word spooky because he could not explain why these particles were like seemingly teleporting. Yeah. So, okay, last thought. Today we have a new model of the atom, and we're like getting way beyond where Science 9, like again, story time with Chris. We're getting into some pretty deep physics and chemistry stuff here. So I'd like you to know some of this stuff, but like if you don't understand it, that's okay. Like it took scientists years to figure this out, and like you can take entire courses on this. I'm giving you like the Cliff Notes version, if that makes sense. So the current model of the atom is known as the quantum model. You've probably heard that word before, like quantum stuff. And quantum theory stuff is amazingly cool. I love teaching this stuff to my physics 30s. Like it is weird stuff. The idea is that these electrons, they're not necessarily particles moving through space, but that the electron is kind of like everywhere at once. It's a weird idea. Let me show you a picture. Rather than believing that the electron is in like one spot right here, the theory is that the electron is like somewhere inside this like bubble. Okay. First thing I need to point out, remember this picture I had right here? This is like a flat picture, right? This is like in 2 dimensions. But like the world isn't in 2 dimensions, it's in 3 dimensions. So like imagine that these are like balloons, and all the balloons are like tied together in a knot at the center, right? What the current model is that we think that the electron lives somewhere inside this like cloud bubble. But here's the problem. As soon as we look for the electron, it's gone. I want to explain why this works. The best microscopes and the best tools we have, they're known as electron microscopes. And what they basically do is they shoot electrons at things. I want to give a different analogy. Imagine that you were blind, and you had to try to figure out your way around. How do you know how to not run into things if you don't have a friend, right? Well, maybe you have like a stick, right? Like a stick, and you kind of poke the stick in front of you, and if you feel the stick hit something, you know there's something there. Does that make sense? So imagine that same sort of scenario, only like, imagine that what you're going to do is you're just going to throw something in front of you. And if you throw a ball in front of you and you hear somebody go, ow, you go, oh, there's somebody there, right? And imagine you were constantly doing that. So you threw something in front of you, and you listened, oh, there's nothing there, I can walk that way, right? That's what an electron microscope does, is it shoots things, and basically, as the electrons hit things, they either bounce backwards or they deflect to the side, and we can kind of get an image of what's going on. Sonar and X-rays, they work on very similar principles. Either the thing you're shooting goes through it, or it bounces back at you. Does that make sense? Here's the problem with electron microscopes and electrons. As soon as the electron microscope, the electron hits an electron, it actually causes that electron to move. Imagine I threw the pen at the wall. Is the wall going to move all that much? No. But imagine I threw the pen at a second pen. You know what's going to happen is as soon as the electron microscope shoots an electron at an electron, it's going to cause the electron it shoots it at to move. And so we can actually never really know where electrons are. It's actually very paradoxical. We can know where they maybe used to be, but we actually can't even know where they are. More than that, even the presence of light causes electrons to move. We've discovered this in physics. And so if light even ever tries to come in contact with an electron, that light actually causes the electron to move somewhere else. When the light's turned on, did you guys get blown away by the light and get knocked backwards? No. Electrons do actually. Electrons are so small that even light causes them to move. Turn the light off and turn the light back on again, and all of a sudden the electrons are in new spots. And not only that, but they teleport to new spots, which is crazy weird stuff. So what I need you guys to know is that the current model of the atom is this thing called a quantum model. And if you just memorize just one thing, I want you guys to know the idea of a cloud, where they believe that somewhere in that cloud is the electron. And we don't even know where it is, because we can't even find it. As soon as we look, it's gone. If you found this last little bit kind of confusing, that's okay, because most people do. But if you found it really cool and fascinating, talk to me. I'll share more about what we believe matter is made out of. Because really, this is what scientists are currently doing. They're trying to figure out, well, what are electrons made of? And what are those made of? And what's that made of? And like I said, the current end game right now is string theory. But I bet you in 50 years, we'll be trying to figure out what the strings are made of. I want to end with one last thought here. I have two bolded words on there. The current model of the atom, then, involves protons, neutrons, and electrons. And that's where we're going to pick up a little bit next week. These are known as the three subatomic particles. I want to go back to where we started again, Democritus. Democritus had this idea that you could not cut things in half. He was wrong. You can. And we actually know there are things called subatomic particles. Remember, an atom is indivisible, but these are what we think things are made of. And so the basic idea is that somewhere in this nucleus, we have things called protons and neutrons. You guys ever heard of those before? Okay. Protons are positively charged. Neutrons are neutral. I'll use a 0 for that. And electrons are negatively charged. And the basic theory is the protons and the neutrons are stuck in this little nucleus, and the electrons are somewhere. But we can't even find them. As soon as we look for it, it's already teleported somewhere else, which is this is where science fiction gets its start, actually. So, and I think that's it. That's story time with Chris. What do you guys think? It's interesting stuff. Okay, so here's where we go from here again. I've got about 20 minutes I can give you guys to kind of start working on things. I'd like to suggest that use this last 20 minutes. I know yesterday I kind of gave you guys some free rein. Most of you, it was okay. Most of you, you printed off some notes and you kind of called it a day. Why don't you now start taking some time today and tomorrow to work on your assignment? Okay. So let me show you the assignment questions. You should start working on these. You can write them by hand if you like. You could also, if any of you want to type them out, if that somehow works, typing works well. But let's look at a few more of the questions on your first assignment. Okay. Many of the first questions are on things like classify elements, compounds, and mixtures, or what Wemyss symbols do you know about? Okay. But now the more recent questions are things like, what were the alchemists trying to do? So hopefully you remember me talking about it. If not, rewatch my video, or ask me, right? Here's the question. Why did the discovery of electrons mean that we had to change Dalton's model? What was Dalton's model again? What did Dalton think stuff was made out of? Just an atom, a marble you couldn't break. But as soon as we found an electron, we knew there must be smaller stuff than that, yeah. Or Rutherford. I want you to talk about what Rutherford's experiment was. Okay. So if you guys can start working on some of these questions, that's what I'd like to suggest you do today and tomorrow. Stop when you get to question 13. Okay. Question 13 talks about the periodic table. We're going to do that next week. Okay. But this should give you some stuff to work on in the meantime. Okay. So please don't procrastinate. Even though you guys have the freedom now to go somewhere else in the building, do something else, don't waste the time, okay? Start doing a little bit of this stuff. We need to get going on our new unit. Sound good? Okay, you guys are free to go somewhere else if you want, though.